In this video, we're going to talk about the rules for when you can sum forces or moments. This is one of my favorite topics in statics because it's so useful. It's so useful for understanding force and moment systems. So we're in chapter 4, and in this video, we're going to be going through section 4.7 and 4.8, which is simplification of a force and couple system and further simplification of a force and couple system. But I've decided to title this Rules for Summing Forces and Moments, and you'll see why. So personally, I found it confusing when I was going through statics in college. You know, forces are vectors, moments are vectors. You can treat them as vectors, you can sum them, multiply them, use the dot product, cross product. You can treat them as vectors. But there's restrictions. You can't just be given a solid body with all kinds of forces all over the place on it and just start adding forces. And I didn't feel like I ever got a full explanation, a full clear explanation on what exactly the rules are. When can and can't you add forces? When can and can't you add moments? Everything like that. We're going to address all of these questions in this video. Okay, so it might be a little confusing because the title is Simplification of a Force and Couple System. It's not talking about any rules for adding forces and moments. Let's just get into this section and I'll explain as we go. Sometimes it is convenient to reduce a system of forces and couple moments acting on a body to a simpler form by replacing it with an equivalent system, consisting of a single resultant force acting at a specific point and a resultant couple moment. A system is equivalent if the external effects it produces on a body are the same as those caused by the original force and couple moment system. Okay, so this sentence is important because, as we've already talked about in previous videos, one of the factors that's going to come into play on whether or not you can add a force or moment is that force or moment a fixed vector, a sliding vector, or a free vector? And another thing that took me a while to understand was, how could something really be a sliding vector, right? So let's come here. The principle of transmissibility. This states that a force acting on a body is a sliding vector since it can be applied at any point along its line of action. So all forces on rigid bodies, and this is not just in statics, but even when we get to dynamics with moving and accelerating bodies, all forces are sliding vectors. And what this is saying is that you can slide a force along its line of action, and no matter where you place it along its line of action, the external effects it produces on the body are the same no matter where it's placed along its line of action. The system is equivalent. Now, this was confusing to me because when I think about real life, if I'm pushing something or, anything I'm doing in real life, it doesn't seem that way. If I pull on something at one point, and then if I imagine going like to the opposite end of the object and pushing on it, pushing is different than pulling, right? You can break something if you pull on it, but if you push it, it doesn't break. Things like that. The key to understanding this is you have to think about it from just a pure static analysis. Like, think about it just from strictly the standpoint of the type of problems we work in this playlist, in this textbook. Just from a pure statics, free body diagram, rigid body standpoint. This is the idea. No matter where you place that force along its line of action, when you do the static analysis and you solve for the forces at the supports, or in dynamics you solve for the resulting acceleration or motion, no matter where you place that force along the line of action, you're going to get those same reaction forces. You're going to get that same motion. The external effects it produces on the body are the same. In this context, the external effects of a system refer to the translating and rotating motion of the body if the body is free to move, or it refers to the reactive forces at the supports if the body is held fixed. That's the idea. Now, yes, sometimes if you pull on something, it might break it, but if you go to the other end and push on it, it doesn't break. That's not static analysis. You're looking at the deformations. Okay, so they demonstrate here, they give an example of how a force is transmissible, or in other words, it's a sliding vector. So you have a person holding a pole, there's a force at the end. You come here and you apply that force at this point B to the right and to the left. So there's essentially no force applied. These cancel each other out. But you can, instead of canceling these two, you could cancel these two. And now you're left with a force here. You just moved that force. You just slid that force. Okay, now before we move on, let me backtrack and remind you of what we already know about moments and forces in terms of sliding vectors, fixed vectors. Okay, so all forces are sliding vectors. In rigid body mechanics, all forces are sliding vectors. And we also saw in the particle equilibrium chapter that it seems to be that if the lines of action of the forces meet at a point, you can slide those vectors to that common point and sum the vectors and put the resultant force at that point. But that was for like these specific particle equilibrium problems. We didn't really expand on that. We haven't looked at, well, what if you have forces that meet at a bunch of forces that meet at a point, but also moments? So we haven't really established what the exact rules are. Okay. Now, another thing I want to point out real quick is whenever we learned about summing vectors, you know, when we were just talking about vectors in general, to sum a vector, you put the tails of the vector together. Now, there is the head to tail method of summing vectors, but in rigid body mechanics and statics and dynamics, in order to sum vectors, you need to be able to put their tails together, either through the use of sliding vectors. So you can, in particle equilibrium, you could slide the vectors and get all their tails together, so you could sum them. Or if you had a free vector, you could move it and put its tail where you want, and then you can sum the vectors. If you can't put the tails of the vectors together, of the force or moment vectors together, then you can't sum them. Okay. And that's pretty much what we learned when talking about vectors in space, the vectors in space video. We did do the head to tail method, but you first had the vectors together, their tails were together, and you said, okay, we're going to sum these vectors, and you could leave their tails together and use the parallelogram method, or you could use the head to tail method, get the resultant vector with its tail also at the tail of the two vectors, and then kind of bring that original vector back. Right? It was kind of implied that the vector tails, if you're summing vectors, their tails are together. Okay. Now, what else? We learned that if you find a moment about a point, a moment of a force about a point, what you get is a moment vector, and it's a fixed vector. It's fixed at the point you found the moment about. You can't just get that moment vector and put it wherever you want. It has to be at that point. We also learned that if you find a moment of a force or resolve a moment about an axis, so the moment about an axis, that's a sliding vector that can slide along that axis. You can apply it anywhere along that axis. And then we learned the moment of a couple is a free vector. Okay, and again, I just want to reiterate, the sliding, fixed, free, what this means is that you can slide it, move it, or you can't move it because you can't change the system, right? You have to make sure the system is equivalent to the original system. You can't just move. If you calculated the moment vector about a point and you moved it, you wouldn't have an equivalent system anymore. But for a force vector, you can slide it and the system is still equivalent. And that's what we're about to talk about in this section. There's different ways you can manipulate forces and moments without changing the system. And so once we go through all of these different ways you can work with forces and moments and without changing the system, you're going to have a really good intuitive sense of the rules for moving and summing moments and forces on a body. Okay, so we talked about how you can slide a force. A force is a sliding vector. That's what the principle of transmissibility is about. If a force or a moment vector can slide, then it's transmissible. We can also use the above procedure to move a force to a point that is not on the line of action of the force. Okay, wow. That's very interesting. Think about what this just said. There's a way that we can move a force to a point that is not on the line of action of the force. So what they're saying is we can move a force wherever we want on a body. There's a way to do this, and the system is still equivalent. Okay, so how do we do this? Let's come here. They want to move this force to the hand. How do they do that? Well, you put of that same magnitude force acting down and acting up. So nothing's changed, right? Now you might be saying, well, yeah, you're compressing, you're crushing the guy's hand. Not for the case of the rigid body analysis. As far as statics is concerned, this does nothing. Okay, but if you look, we've got minus F and F. We have a moment, a couple here. So you can turn this into a couple, and now look, your force has moved. You moved the force. You have that force move to a new spot, but you just need to put a couple there. So, but this is definitely a couple. This is a free vector. Okay, but this is just a simple 2D case to illustrate the concept of how you can move a force. Let's look at this in general, in a general 3D case. So here's a body. There's two forces acting on it in a couple moment. And just to illustrate something, I'm going to put another force here with a position vector from point O to this force. So what they're trying to illustrate here is how you can take a system of forces and simplify it down to one force at a point and a couple moment at that same point. You can take any system of forces and convert it into one resultant force and couple moment at a point, and you have an equivalent system, right? So here there's forces. They have forces, and the force I added, and a couple moment. But there's no moments. So we have a couple, we have forces. What about the moments? Just the general moments about a point. Well, that comes from a force, right? You have the moment of this force about anywhere you choose. You have the moment of this force about point O, but that comes from the force. A couple moment is its own thing. So that's why they have like a general state of loading here with some forces and one or more couples. And what they do is, if we ignore the force I added, they move this force F2 to point O. They move F1 to point O, which is off the line. It's not on the line of action of the force, these forces. So when they do that, they have to add the corresponding couple. How do they do that? Well, what they're doing is you kind of imagine that here's a line passing through O that's parallel to the F1 line of action. So you put this as minus F1 here and plus F1 here. Now, this minus F1 and this F1, that's a couple. You determine that couple and then get rid of these forces, and you're left with F1 here and the couple moment. And so you can determine the couple moment by just taking a position vector from the point of interest to any point along the line of action of F1, do that position vector cross F1, and that's the couple moment. I mean, you could technically do a position vector here, right? When you think about how we defined couple moments, it's any position vector from the line of action of the negative force to the positive force, R cross F. But you can just go ahead and use this position vector that's its tail is at the point of interest. Okay, so they do that for F1, they do that for F2. They move, so they've moved F1 and F2 to the point, but with each one of those, there's a couple vector. Here's the couple vector associated with force 1. Here's the couple vector associated with force 2. And then here's a couple on its own. You just move, it's a free vector. You move that to point O. And so they get all of these vectors with their tails at this point. Now you can't add a moment in a force vector. Like you have to, right? You can add moment vectors. You can add force vectors if their tails are together. So they add all of the moments, all of the couples, and they get this resultant couple, and then they add all the forces and they get this resultant force. So what you can see is you can take any body, any general body, and it's going to have any type of loading on it. It's going to be some mix of forces and couples. Again, you might say, well, what about moments? What about regular moments? Moments come from forces. You see the body. You haven't calculated any moments yet. It's just a bunch of forces all over the place, and then you can have couples. If you want, you can reduce that down, simplify it to at one point there's one force, and at that same point there's a couple. Now you might be saying, well, wait a minute, why does this couple have to be at point O? It doesn't actually. This resultant couple can be anywhere. It's just common convention when you're doing this to put the couple at point O, but it absolutely could be anywhere. It's a free vector. Okay, so why did I draw this? I just want to illustrate that if you wanted to, you could say, I don't want to move F3. I want to leave it there. I'll move F2 and F1 to point O and move the couple moment to point O, but you could say, I don't want to move F3, but I want to put the moment of F3 about point O at point O. So you do that. You say R3 cross F3, and you get this moment vector. Right? It's going to have a rotation. You don't have to put this rotation sense, but the rotation sense would be like that. And then, but F3 is still here. Okay, so now this is just another moment vector that it's at point O. Its tail is aligned with these other moment vectors. You could sum M01, M02, M and M3 and get a resultant moment. Now this resultant moment, though, is not a free vector anymore because you've got this fixed vector mixed in with it. And then also, just to point this out, you couldn't say, okay, this is the moment of F3 about point O. Let's calculate the moment of F3 about point P as well and put this moment over here. And this is M3P, this is M3O. No, because if all of a sudden you apply two moments, like you could do that as a separate analysis. You could analyze the effect of force 3 about point P, but you can't have both of these on there at the same time. That's implying that you've got two force F3s acting on the body. You can't have these acting at the same time on these 2 points, these moments. Not at the same time. Yes, F3 is causing rotation about point P and point O, but if you applied these two moments, one to point P and one to point O at the same time, you're implying that there's two F3s on the body. You would have to remove this M3 here and then consider the effects of the rotation that F3 is causing about point 3 separately. Okay, here they give an example. It says the weights of these traffic lights can be replaced by their equivalent resultant force. So here's the weights of the traffic lights, resultant force in a couple moment at the support O. So put the resultant downward force as well as a couple moment. And it's saying that in both cases, the support here, so this supporting pole has to resist that vertical weight and that tendency of rotation, that tendency of wanting to twist it, that tendency to rotate, that moment. Okay, so we just saw that for the most general case, you have a body with a bunch of different forces on it, with some mix of forces and couple moments. That's as general as it gets. Again, there's no moments. Moments come, you apply the moment based on the force. So in general, you're going to have a body that has a bunch of forces on it and potentially couples as well. You can reduce that down to one force at a point and with a corresponding couple moment at that same point. The couple moment doesn't have to be at the point if you don't want it to be. In this section, they show some special cases. So what if you have a concurrent force system? So all of the forces, the lines of action of all of the forces meet at a point. Well, then you can reduce that down to just a single force at a point. There's no couple moment or anything. It's just a single force at a point. So this is like the particle equilibrium case, right? We saw this with particle equilibrium. All of the forces acting on a body, in the body's in static equilibrium, meet at a point, and you can draw the free body diagram as just a point with all the forces acting on that point, and then you do a vector sum, get the resultant vector, and place it on that point. Now, we did talk about how, if that point is the center of mass, then for the dynamic or the static case, you can use the particle free body diagram model. It's that particle model. If it's not the center of mass, if it's static equilibrium, you can still use the particle model. But if it's the dynamic case, then it's not a particle model in that case. We talked about that before. But just to point out, even if you had a bunch of couple moments or a bunch of different forces, and you had 10 different forces, but 4 of those forces, their lines of action met at a point, you can still simplify those four forces separately and just put the resultant force at that point for those four forces. Why is that? Because forces are sliding vectors. As long as you can slide the vector, two vectors to where their tails are at the same point, you can sum them and put the resultant there. Okay, another special case, what about a coplanar force system? We saw how if it's a purely concurrent force system, this can be simplified even further than what we saw in the general case, where you can just have one force at a point, no couple. What about the special case of a coplanar force system? So if we come here, here's a general case. They bring all of these forces to point O, and then what happens is this resultant couple moment, right? To bring all those forces together, you also get a resultant couple moment at O. But what you can do is you can move FR off of point O, a distance D that results in the magnitude of the couple moment. And also, if you noticed, let's say that you came to this planar problem and there was also some existing couples in the general case. Well, what do? You simplify that, just like we saw in a couple of pages ago. You simplify that to a net resultant force and a couple moment at the point, same exact way. You just add those couples, that couple or couples to this resultant. Same thing. You're just gonna move FR off whatever distance D you need to account for that couple. Okay, another special case, a parallel force system. What if you come across something like this? All of the forces are parallel. Okay, well, same idea. You can move all of the forces to point O, to whatever point you want, and then just do, it would be like R cross F1, R cross F2, R cross F3. You know for sure that the moment axis is going to be in the plane of the plate, but where exactly the moment axis ends up being just depends on, it depends on the vector sum, right? It could be here, it could be here. You need to do the vector sum. So like, this might be confusing, but so like R cross F1 is like, in this direction. R cross F3 is like in this direction. R cross F2 is like in this direction. Right, that's the perpendicular directions to the R and the F's, and and then you take this vector sum and you get the resultant couple moment. So okay, you reduce this coplanar force system to a resultant force and couple moment at a point, but similar to the coplanar case, the resultant force and the couple moment are perpendicular. So you can reduce it even further to just a resultant force by moving the force a distance D perpendicular to the axis, to the moment axis, that creates the same couple, that creates the magnitude of FR times D is equal to the couple moment. Okay, but again, these are special cases. As we talked about, for the most general case, all we could do was reduce to one force at a point with a couple moment at that point. In the couple moments in an arbitrary direction, and the forces in an arbitrary direction. There is a way to simplify that general case, though, a little bit more. This is how. So here's the general case. You've got a couple moment at the point and a resultant force at the point. What you do is you break up the couple moment into components that are parallel to the force vector and perpendicular to the force vector. So this is M perpendicular, M parallel, it says. Then you can get rid of M perpendicular by moving the force vector off of the M perpendicular axis like we just saw with the coplanar case. Okay, now, but M parallel is a free vector. Just like M perpendicular is a free vector, M parallel is a free vector, the net couple is a free vector, but we got rid of M perpendicular. You can move M parallel to point P, no problem. And you get this couple moment and force vector along the same direction at the same point. This is called a wrench. Okay, a wrench is the simplest system that can represent any general force couple system on a body. Okay, now let's work some example problems so we can make sure we have a full understanding of these concepts.